I select this title.
So Vittorio, it's not in presentation mode.
Ah, sorry. Can you see completely the screen? Probably yes. I decided to use the title of 60-year progress because just in 1959, 62 years ago, by precision, a paper was published by Alan Cohen and Colkins, two rheumatologists working in Boston, that described the first electron microscopy analysis of a heart infiltrated by amyloid. And I think this paper was the first paper in which we move from a microscopic analysis of amyloid material into a submicroscopic level. And now, after 62 years, we have amazing improvement in our capacity to look at this material at the, with the resolution at the atomic level. The material, however, is a very difficult material to be analyzed. Here we have a classical histology of myocardium infiltrated by amyloid. You see this pink staining is just amyloid infiltrating the fibrocellular muscle. And this material is, has some tinctorial properties that are still in use in our laboratory to make the diagnosis, but is extremely difficult to be analyzed because the fibrils, the material is intertwisted with the natural material of the extracellular matrix. So is an extremely difficult material to be analyzed and to separate from the remaining material. So it's quite expected that the progress in understanding the structure and possible the mechanism of formation and function of this amyloid run in parallel with the improvement of technologies and the availability of new tools. Several discovery on the side of technology in the lower part of the slide were associated to better knowledge of this material. The material was already known in '59, but was not characterized. And you can see here how a few discovery on the technological knowledge can have an impact on the understanding on the mechanism of formation of amyloid. I highlight, for example, all the study on folding and the dynamics of folding that now are so important in trying to dissect and elucidate why globular protein, for example, can be transformed into fibrillar structure. And the investigation of amyloid is, and somehow also have broken some postulate of protein biochemistry. For example, the idea that just one single sequence can have just one single conformation. So there was a parallel growth of technology and knowledge. And I think the acquisition of knowledge on the disease follow this common thread of knowledge that is similar to other type of disease. So we start from the disease in patients, and of course, more we know about the natural material and the structure and the basic diagnostic procedure improve, more we know and more we are become able to generate some model of the system. So somehow more precise we are in characterizing the material and more able we become to translate in simple or more complicated models trying to recapitulate the disease. And when we recapitulate the disease in model, of course, we have the possibility to interfere with the disease, and we can explore both diagnostic procedure and also some new drugs or therapeutic approach. But we should not forget the sentence of Richard Feynman that in completely different context say that we don't understand completely phenomenon if we are not able to recreate somehow in a different environment. So I think we can follow historically what we have the progress of the knowledge of the disease, starting from the real beginning when the material that was seen by electron microscopy so well by the paper of Cohen was extracted from the tissue. And this, I think, is a fundamental paper, has a lot of meaning for me, about how we study and we understand the disease. In Mordecai Pras in Edward Franklin laboratory at the NYU was able to solubilize some amyloid material from a natural tissue. And just having this material available, I think we should remember the paper by Glenner, was working at that time at the NIH in Washington, that described for the first time the possible structure of the fibrils by X-ray diffraction, and discovering the interstrand, intersheath space that is the common motif of the amyloid fibrils. But big advances came when the group of Glenner was able to determine the sequence of this material extracted from the fibrils that was identical to the fibrils to the protein that circulate in plasma of the same patient. So this was an extremely important demonstration that probably the material, the amyloid material, was caused by a circulating plasma protein. And I put the term creation as a title of this slide because somehow having more information about the composition of the material, both from the natural fibrils and the circulating protein, made possible to imagine to recreate the fibrils in vitro. And this was a very important step because the fibrils was recreated by a group of, in a triangle between New York, Boston, and Washington, the NIH, where some distinguished fathers of this disease were working. So the idea to recapitulate and create in a model was already present in the early 70s in the story. And I think we should pay a tribute to this paper, to these people. Reinhold Linke is still active in Germany, and the other, unfortunately, we are missing. And I like to remember that George Glenner in 1984 is the person that for the first time discovered the nature of the A beta in the Alzheimer plaque, because he was able to purify and sequence the fibrils from the brain. And the paper was published in Biochemical, Biophysical Research Communication, a journal that now is as an impact factor of 3. But this finding, this precise characterization of the nature of this protein was essential for all the studies that followed this discovery. And I like to say that when you precisely characterize the protein responsible, a big shift in the approach to the disease can be induced. And I think the discovery that the protein, the fibrillar protein of some patients was caused by the circulated immunoglobulin made the shift from rheumatology to hematology. And this is amazing impact, because when the hematologists took the action in the approach to the disease and using their own tools, you can see from 1986, when you have the survival curve of patients on that years, you see how the shift in the discipline that take care of the patients can have a massive improvement. And you see here in the clinical trials in the last few years, you see the survival of the patients, how it changed along the years. So I think to the precision by which we characterize the material is essential, and we already have demonstrated this is important. And if you look at the framework I presented at the beginning, when you are able to characterize better the system and demonstrate, you can recapitulate in vitro, you can include the possibility to have therapy. For the treatment of light chain amyloidosis, was not necessary to have any model, any animal model for describing or hypothesizing a better therapy. But sometimes, even if you have information on the structure, you are not so successful. So I will present a couple of stories in which, even if you characterize the material, the translation into better cure is becoming possible or fail. This one of the failure when following the discovery that in amyloidosis there is a lot of deposition of glycosaminoglycans, and Bob Kisielewski was one of the father of the disease, hypothesized that treating an animal model developing this amyloidosis with the inhibitor of glycosaminoglycans, you can cure the disease. And the animal model was very successful. The paper was published in Nature Medicine, has generated a great expectancy for the treatment of the disease. And it's interesting that a company have developed this approach, and the first clinical trial in 2007 in more than 180 patients was very promising. And you see here the endpoint was reached with the compound in comparison to the placebo. However, in 2014, for a higher number of patients, the trials was not so successful. And it's interesting that the company that bought the previous company stopped the trial, and all the information were missed about the failure and the reason of the failure. It was just limited to a press conference in which it was announced that the endpoint was not reached and the trials. So far, after 5 years, we don't have any information on the reason, the molecular reason for the failure, or the difference between the first clinical trial and the second clinical trial.
Just 3 minutes left.
Yes, okay. I will skip a few slides regarding the discovery that another important protein as therapeutic target was used by my group in UK by Professor Mark Pepys, focusing on serum amyloid component, that is an ubiquitous component of amyloid fibrils. And I will say that Mark Pepys has brilliantly used this discovery for a diagnostic procedure, and SAP can be a good scintigraphic tool for looking at the amyloid, but was not satisfied at that. He decided to move into a therapeutic tool, and in a mice model, antibodies against SAP was very, very effective in removing the amyloid from the organ. And the clinical trials was established with GSK and was very successful, because in 2 papers in New England Journal of Medicine in 2015 and in Science Translational Medicine in 2018, the results were confirmed for the removal of amyloid from liver and other organs. However, in 2017, we had a few side effects, and the perception that the amyloid in the heart was not so easily removed in comparison to the other organs. And the trials were suspended, and so far, we are not able to have information about the molecular basis of this discrepancy. So I think it's important in this framework to remember that even if we have a flow from patients, and the best flow from patients to models and again to patients, we should be ready to have this red arrow, because are so important to learn. It should be so important to learn from failure, and this sometimes is not so easy. So I will leave you with some open questions that are questions that can be probably raised by the other presentation. We don't know much about the mechanism of tissue localization. We don't know much about the rate of deposition in vivo in different phases of the disease. We don't know exactly if we represent totally the fibrils we extract with the fibrils that we have in the testicular matrix. And I leave all these questions to you, but also I like to present a slide that my brotherly colleague, fellow student, and professional psychoanalyst Giovanni Foresti, sometime when we discuss the uncertainty of this research, is suggesting to me. And we have probably many cases to opportunity to continue and to have to oversimplify the system and probably to publish a lot, but probably the path of truth is more complicated. We should continuously consider that we should work on this difficult pathway. I finished.